Welcome to the Biota Podcast. I'm Tom Barbalet, and today I have the pleasure of talking with Professor David Ackley. Professor Ackley, thank you for coming on the Biota Podcast. I know you heard about this through Twitter. I took a screenshot of the list of questions, I posted it to Twitter, and somehow that
came past me. That came past me somehow, yes.
So, anyway, look, frivolity aside, how did you get interested in the field of artificial life?
I've been doing computing basically all my life since the 70s. You know, it was great fun. I enjoyed learning to program. I enjoyed learning how to make computers do what I wanted them to do. But as I got further along, I always wanted to have something new. I mean, I started getting jaded with what typical programs would do. When I went to graduate school, I started out doing artificial intelligence type stuff and machine learning. And my PhD, my dissertation was in that area, connectionism, as it was called at the time. And that's what I started doing after I finished my degree. But, you know, the honest truth, the story I tell people is that the reason I do computing is because I was trying to make a theory of Dave, an explanation of myself. And if it turned out that a theory of Dave was also a theory of Tom, well, then that's great. I'm happy to share. If it turned out that I was weird in some way, well, I was going to model the weirdness and let everybody else go make their own model. And so I studied artificial intelligence for quite a while, thinking, wow, I'm such a smart person. But I started to think, if I'm really honest, if I'm really clear-eyed about it, you can explain an awful lot more about what happens in a given situation, in a given day, in a given moment, by the fact that these systems are alive rather than the fact that they're intelligent. Intelligence is like the froth on the top of the wave. And if you want to understand the wave, you have to understand what living systems are like, how they behave. And that's how I started turning away from artificial intelligence towards artificial life.
So in that definition is survival versus intelligence, I guess. Can you describe some of your early experiments that led you in this direction?
Well, a lot of it was really just thinking. I think of try to make a model of, like I said, model of myself. I mean, if you say you see a picture, all living systems have certain things they have to do. Survival, yes, but they have to put food on the table. They have to protect themselves. They have to control enough of their physical space to keep their body protected and so on and so forth. And when you start looking for it at that level, you see everything is structured to deal with those issues. And yes, there are cases if you see someone run up to a box, well, this is back in the old days when there were payphones, and pick up a phone and push 9 and 1 on the thing, you would use your intelligence to compute the next thing that was going to happen is they were going to dial another 1. But that's an extremely unusual case, and I started making models, the traditional A-Life models, and a 100 by 100 grid with directly programmed agents and directly programmed plants, and watching them run around. And it was great fun. It was very satisfying to see these things running around and doing things that for a moment I didn't understand. And I would have to stare and say, what the heck is going on there? And then eventually I would understand how that indeed was a consequence of the way I had written them. And then it wasn't so interesting, so I would move on.
As you've outlined, the theory of Dave, the pinnacle, the thing that you're moving towards, what experiments led you more in that direction?
Well, again, that's kind of putting the cart before the horse. The desire to understand myself predates all experiments.
Certainly. But what experiments, if that is the goal, the end goal?
Yeah.
Can you talk a little bit about the work that led you more in that direction away from just traditional artificial life simulation?
Well, it was the artificial life simulations. When I was first doing this stuff to actually publish about it and stuff like that, it was in the 80s, late 80s. At that point, just doing traditional A-Life simulations was exciting enough. And I was working with Michael Littman, who was a student at the time, and now we still work together, whatever it is, 30 years later. But at the time, it was just saying, well, okay, so we simulated evolution. We gave them a genome. They could look left, look right. They could adapt their weights and so forth. The original question I got fixated on focusing on was that when you do learning, you get feedback. You get something from the environment to tell you what's good and what's bad. And in supervised learning, some teacher tells you exactly what output you need to get for some input, and that's great. You try to learn how to do it. But you can have less. You can have a reinforcement learner where you just get a correct or incorrect signal, but it doesn't tell you what the answer is. You have to try things and figure out the answer. So you get less feedback with reinforcement learning. And with temporal reinforcement learning, where there might be an arbitrary delay in when you get the signal, it's even the teacher is even less helpful. You have to figure out what events that you did in your own past were the ones that were responsible for whatever was a good or bad outcome. And so the story that we tell was that we tried to take that to the logical extreme. What is the least helpful teacher imaginable? And what we said it was, well, the least helpful teacher gives you very rare feedback, and it gives you one bit of feedback, and that's your own death. So really all you get from the environment is the fact that somewhere in your past you did something so wrong that you're dying now. And the question is, was there some way that we could actually learn during our own lifetime, given only our own death as feedback? And that was the challenge that Michael and I took on, and it led to the development of ERL, Evolutionary Reinforcement Learning, that puts together two neural networks with an evolutionary framework. And the idea is you have one neural network that looks at the world and tells you what to do, and you have the other neural network that scores your own behavior, tells you whether that was a good or a bad outcome. And the idea is, well, that's like a teacher telling you what's a good or a bad outcome, so you're cheating. But the point is, when you start the simulation, the weights in that reinforcement network are random. So it might be telling you that pain is good, starving is good, whatever. But if that's true, then you will learn not to eat, you will learn to bang your head against the wall, and you'll die young. Whereas if you happen to have a reinforcement function that says something helpful, like go toward food or whatever, then you might have kids and so forth. So we showed that did work, that you could have just coming evolution at the end saying you did something wrong. You could gradually involve a reinforcement function internally, which in turn would let you become better at whatever you are doing during your lifetime.
Does this idea map back onto biology at all?
Well, I don't think there's any question that systems, certainly human systems, but even much simpler systems than that, have some analog to this. When you talk about drives, when you use the hunger drive, fear, the 4Fs and so on and so forth, that is an internal reinforcement function that's guiding the behavior of organisms that was passed down over the years through evolution. And that's what we were modeling.
It is interesting, the notion of simulation as giving additional things to biology as a means of kind of filling the gaps of where biology may be poorly understood. Do you feel that is part of this work? That actually biologists should come back and look at this and then think about where their biological understanding is missing these kind of insights?
I don't know. I suspect there could be such feedback, but I think it's relatively rare. In my experience, the challenge of trying to do interdisciplinary work is that everybody's disciplinary assumptions are very strong and they all conflict with other disciplines. So just like molecular biologists are focused on things that happen during a single life, and they don't really care about evolutionary change, whereas evolutionary biologists really don't care what happens in a single life. They're just so one field completely minimizes what the other field's entire focus is, and vice versa. So it takes a lot of work when you try to do interdisciplinary stuff to learn how to sort of back off your own disciplinary assumptions and be a little more gentle about what's in and what's out. And I think that's kind of true between artificial life and biology. Certainly, I've had conversations with folks, like John Maynard Smith way back when, a story that Dan Dennett tells about the three of us were sitting around a table at the Santa Fe Institute and knocking around ideas about evolutionary biological systems and how you could model them in artificial life models like that. And John Maynard Smith was getting reasonably excited about stuff that we were thinking of like that. And I think that's probably as close as I have ever come to what your question is getting at. So, yes, it's possible, but John Maynard Smith was already a very abstract thinker and sort of interdisciplinary guy all by himself. In my experience, most folks who are doing actual biology, it's a forest versus the trees thing, that they're spending their entire career understanding one leaf on one kind of tree. And they don't really need let's just talk about living things in general. They don't have a lot of patience for that because they're getting down to specific work.
I think what's interesting, particularly through the International Society of Artificial Life, is the periodic discussion of reaching into biology and, finding biologists. And certainly, I'm not sure if you're familiar, I can't think of the name of the team, but there's a Michigan State University team that actually brings in, visiting biologists and things like that. I visited them in 2012 and,
right.
met with some bee folk, for example, which were really...
Right. No, so did I. Yeah. And then that was Charles Ofria's lab. Certainly. And the Beacon Project generally.
Yes.
Like that. They are trying harder than a lot of folks, as far as I know, to actually feed both sides of the biology as well as the computational modeling. So I think you're right. That's a good example.
I mean, I think the thing that excited me there was it was very much your Maynard Smith example, that just by bringing people together, conversations are had, perhaps in tea rooms, perhaps more formalized. And I think that was certainly something that I found very exciting with that group, that I could talk with people that had been fighting for education in schools, that had gone up against creationists in, various court cases. I mean, the plurality that team had was really fascinating. And I think what's interesting associated with the field of artificial life is its ability to instigate change in other areas. So one of the things I wanted to talk to you about, because I thought this was a very good example of how you've reached out of this interdisciplinary problem, is by putting so much information on YouTube. And I think that's certainly how you're well known in a kind of broader hobbyist community, is that you have put a lot of different talks and also your own musings on YouTube. Can you talk a little bit about that as a process?
Sure. I identify as a scientist or a computer scientist, and I did this sort of work, at first, not necessarily saying it aloud, but in my mind, working on the theory of Dave for decades. And as far as I was concerned at that point, my work was done once the paper was published. If the world outside was, not ready to appreciate the pearls of wisdom I was laying before them, that was not my fault. And for much of my career in computer science, at first in graduate school, and then at Bell Communications Research in New Jersey, and then at UNM in the Department of Computer Science, that was great. That was fine. I felt like I was contributing to the base of scientific knowledge with some new angles, things like ERL, which was one of the inspirations for Polyworld, for example, that you've mentioned in your podcast here, and later on, as I got a little older, a little more senior, I started to be less satisfied with just publishing scientific papers. Somehow the world wasn't changing fast enough. And, I finally said, it feels unseemly to be a self-promoter, that if this work is good, then people ought to find it and figure it out. But we're in a space, we're in an environment where the internet and the rise of people, the rise of the amount of communication that's going on is expanding at such a stunning rate that, you could be kind of the best thing since sliced bread, but unless you just have that perfect combination of luck, connections, and everything else all at once, your stuff could easily be forgotten without some help. So I started to feel like I had essentially a parental obligation to the ideas that I had thought up, the pieces of work that I had done, to try to get them out in as understandable and unjargony a way as I could. And so one way to do that was to make YouTube videos and just to record talks I gave and put them up there, just to try to get some amplification, just to, instead of having just the people that happened to be there in the room that day, there would be a chance that other people could find it. And that's how it started. And then the other thing was there was a grant from the National Science Foundation to help support this thing called New Mexico CS for All, which was one of the early programs to help get computer literacy out into New Mexico. Very specifically, by not just teaching high school kids how to compute, but to teach high school teachers how to teach computing to get additional leverage. And we had a grant that I was a little tiny subpart. It was largely run by Irene Lee. It was her vision. She's now at MIT, I think, to build this whole scheme of teaching teachers and then helping that teachers teach the high school students and so forth. As part of that, I was a little small part of it. And one of the things that I ended up doing was making a few videos actually funded by the National Science Foundation on this grant. And so there were basically three of them. The first one was about the idea of hill climbing. The second one was about the idea of pseudo-random numbers. And the third one was about artificial life. And so those I actually put some work into. I developed custom software for visualizations for each of those because, I was funded to do that work. And they came out really pretty good. And they're sort of still selling, on YouTube. They're still finding views. And I think that's really great. And that kind of put the bug in my bonnet to say, you should never do something that just happens and then disappears and is gone. If you're going to take the trouble to make a presentation, you ought to have it out there so that people can find it if they want to.
I think this idea is so powerful, yet certainly within the artificial life community, as I've been a part of it, I've seen parts of the academic community really shy away from this notion of public facing. But in your embracing of it, have you been able to encourage others within this community to start doing the kinds of things that you are doing?
I'm not sure. I took sort of a sabbatical from artificial life for maybe 8 years or so, and I wasn't going to the conferences and so forth. And in fact, a whole new generation of artificial life folks sort of came up during that time whose work I was much less familiar with than I was with the older stuff from before. And then again, around 2008, 2009, I started getting back to the conferences and publishing explicitly in those conferences. And it seems to me that it's happening by itself. I mean, that it is getting more common for people to post abstracts or to write blog posts that abstract the paper once it's a preprint and so on and so forth. And I think that's all to the good. Whether I had any part in that is not necessarily something I would even know. I mean, that's kind of what happens when you put stuff out to let people find it.
I think YouTube is distinctly different, though. You are going head-to-head with makeup tutorials. You're going head-to-head with unboxing, Disney products. I mean, I think the plurality of this thing is absolutely fascinating, and your ability to reach a far broader audience through YouTube.
On the one hand, thank you, and I agree with you. But on the other hand, I'm talking thousands of views. Unboxing videos are talking millions of views. That's three orders of magnitude between us. So they really shouldn't put us in the same sentence as far as the impact that I'm having. I'm happy for everybody who finds the stuff. I'm happy for everybody who gives me some little feedback or a comment or whatever like that. But it's still a tiny, tiny, tiny thing, which sort of makes it a little bit scary to think that if that's tiny, well, then what is the impact of science, of the sort of secret A-Life stuff where it's just being read by a very small community of like-minded folks? On the one hand, that's really great. Because when you have a tiny community, you can establish common language, you can establish your own private jargon, and you can communicate very effectively. You can say, oh, well, it's a evolutionary strategy is modified with a thing and a genetic version, like that. And that's great. But then at the same time, you just excluded 99.99% of the universe by using that jargon. So I think, it's on everybody to do a little bit of the work of reaching out of their tiny little disciplinary communities and trying to find language that'll reach a little bit more broadly. And certainly, what you do with the Biota podcast and so forth. And Tim Taylor, who you've spoken to a couple of times, has done a lot for the science popularization and artificial life. And so have lots of other people. And I think that's all to the good.
I think what interests me in particular associated with YouTube is that it has the ability for folks that are curious, as you say. So this is why the distinction between your video and the unboxing video. But when you look at ideas that are now being, particularly in industry, being made completely mainstream, ML, for example, ML is now something that people that had never used ML historically, small-scale app developers can now add ML into their programs. But there is very limited information available online about how this actually works. And what's fascinating looking through your catalog is that you have a couple of videos on ML that actually fill some of the gaps. I've recommended to coworkers that are picking up ML now how, your videos are useful in this light. The nature of putting information out to the general public is very different than making papers available online. Do you get the sense, do you get students through your YouTube videos? Do you get the sense that your YouTube videos are encouraging people into the field?
I certainly have gotten feedback. Usually they're already students and they're doing computer science, they're doing perhaps biology or biological information processing or whatever. But like many, many people, they have they're looking for a theory of Fred or Tom or Bob or whoever they are. So they find some of the artificial life stuff and they get way excited about it. And they get in touch. And that makes me feel great. It makes me feel like I had some positive impact like that. I have ambitions for much larger impact still, but hey, I will take it.
Let's talk about this ambition since you raised it. Given 10 years, given potentially unlimited funding, given a wide variety of possibilities, where would you like to take this thing?
So I have a specific mission for the last 10 years or so that I am convinced that we as a society need a fundamentally new computer architecture. And this is not an idea that I invented. The idea goes all the way back to John von Neumann in the late 40s, the guy who's credited with sort of starting the kind of computing architecture that we have, the idea of CPU and RAM. And he said, that in the near future, when computers get to 10,000 gates or so, we're going to have to reinvent computing to allow for the possibility of failures. We're going to have to expect hardware not to be reliable. We're going to have to limit the length of our programs so that they don't accumulate errors and so forth. And I think he's right. But I think computer science and the computer industry has ignored him for 80 years and has continued to just insist that computer hardware, its job is to be 100% reliable for whatever scale of computation, however much RAM you've got, however much runtime your program is going to run. It's the hardware's job to do that 100% flawlessly with absolute repeatability. And I think that attitude has to change. I think just like von Neumann said, we're going to have to reinvent an architecture that will allow for hardware to fail. And I believe there's a huge number of steps from there. Okay, that's just the very beginning. But then there's a ... about the consequences of saying, geez, how the heck do you write a program if you say if x less than 0 and x is less than 0, but it takes the other branch anyway, just because? It's very hard to imagine how you would actually program that. That is a level of uncertainty and failure much more profound than just the input doing something weird or a network thread failing to respond. That's the kind of uncertainty that we deal with in computing today. I'm talking about something much more intimate, inside the host, inside the processing units, stuff going wacky and software having to deal with it. And there's a carrot and a stick. And for me, the stick is that we are never going to build computers that are actually secure using what we're doing now, using CPU and RAM, plus the assumption that hardware is 100% reliable and deterministically executing. The carrot is that once we give up on that, we can now create computers that can be as big as you want. You don't have to decide how big the computer is at the beginning. You can just say, okay, well, I need about, I don't know, a square yard of computing or something like that. And if that turns out not to be enough, you can plug more of it in even while the program is running, because software is going to take much more of the responsibility for reliability, for landing on its feet, for getting something useful done, even when the unimaginable happens. And as a result, once we work our way all the way through that and we say, how the hell could you write software that could survive under those circumstances? You end up reinventing artificial life. The software that is going to survive on this new best effort computer architecture is going to look a lot like artificial life. Little artificial chemistry, making little molecules that form artificial cells that reproduce themselves. So in case one of them gets destroyed, there'll be another one that can do the job, and so forth. That's the big picture.
So I'm going to play devil's advocate here.
Go for it.
Because I've certainly enjoyed your videos on this particular topic. But certainly working in industry, my feeling is the paradigm has moved, right? This was something which was probably easier to characterize maybe 2 decades ago. But what you're dealing now with cloud computing and a lot of the methodology, the notion of instances, for example, but a lot of the methodologies that come into contemporary computing create stability through testing and then adjustment associated with failure. And it's done on such a vast scale now, the notion that the underlying hardware needs to have a very particular paradigm seems to me to be beautiful and very hobbyist-centric and something clearly that the maker community can embrace.
That's fighting words.
But I said I was going to play devil's advocate.
It's okay. I'm just letting you know.
It doesn't seem to be the concerns that were had 2 decades ago associated with these kind of problems haven't actually manifest themselves in a profound sense. What do you say to that kind of...
Why is it that we cannot make computers secure?
My perspective is actually we, to a high level, are able to make computers secure sufficient for our general existence.
Really? Okay. I think we're living on the kindness of strangers, in fact, that we haven't seen much bigger and much more significant disasters, even though we see them every damn day in terms of, account compromises and theft of information and so forth, that somehow we have brainwashed ourselves into thinking that is okay.
Well, no, I don't think
millions of accounts a year. It's staggering, and yet we take that as business as usual.
No, I think our government representatives take that as business as usual because they're lobbied accordingly. I don't think individuals feel that. My perspective is...
so how are we going to fix that?
Well, in a majority
you say things
of cases,
are okay.
In a majority of cases, it's to do with contractual relationships between the entities that own the information and the fact that there are loops in the contractual information. So my perspective is that this isn't a fundamental hardware problem. This is actually associated with the other systems that we live in, the non-computer-based systems that we live in, associated with the legal system and a variety of strange manipulations. But that, I think, blaming technology to create new technology is a wonderful way to talk about creating new technology, but I don't think it's the technology that's at issue here. It's the nature of all the other, bureaucracy that is around the implementation, particularly with regards to these kind of failures.
I certainly go partway with you. For example, here's something that I think is completely no-brainer that the industry will squawk like a chicken with its head cut off. I'm in favor of software liability law reform. So you should not be able to sell software for money and disclaim responsibility for arbitrary software failures. And so I agree with you. That's an example of the regulatory and policy regime that has a role to play in the computer failures that we've got. And similarly, the fact that the people who gather our private information on their giant websites have very little incentive to actually protect it because there's very little downside for them protecting it.
It's all upside for them selling the information. Without question, business models for a majority of these companies is based on selling information.
Right. But where I disagree with you is that suppose we had my fantasy regulatory realignment, that there was actual consequences. You had to pay money to the people if their information was leaked, and you couldn't disclaim responsibility for bugs in your own software. That is not enough. Even if you did that, you would be essentially facing an impossible problem trying to make the technology secure. And I'm not a regulatory person. I am a technology person. So I'm trying to push the ball in the dimension that I can push it.
We're skirting around the name here, so let's just put Movable Feast Machine out there, because this is basically the technology that you're describing. For folks
That's
listening
the one I'm exploring.
that haven't heard about the Movable Feast Machine, what is the you've basically given the elevator pitch. What, in addition, describes the Movable Feast Machine?
As I suggest, the paradigm of central processing unit and random access memory, along with the idea that execution is deterministic, is already, just those three assumptions, is already a recipe for disaster. And it has lots of consequences. And again, I understand that this is a big ask of the existing computing community. That's why nothing has happened on this for 80 years. But as far as I can tell, that's where the problem actually is. And, as a personal story, in the early 2000s, I was working on computer security, and we were trying to take sort of biological inspiration for diversity and the sort of stuff that living systems do to try to make some progress on the problems of computer security. And, the basic thing that actually worked was the idea of diversity, about software as it comes out of the box and gets run on these things is a monoculture. The software at the time was essentially completely identical on all possible machines. So once you managed to find a hole, a flaw, an attack on one of them, you could take over giant swaths of identical clones. And so we published some early work on automatic diversification of software. And the original thing that we did was to add random size padding to each stack frame when a subroutine was called, so that your attack against a buffer overflow on the stack would only work if the thing matched up. And that was great. And, it's easy to forget that at the time, people within the industry were completely freaking out about that, not about the security, but about the fact that we were taking it upon ourselves to say we could want to do things like rearrange basic blocks within a program or add padding to the stack, which wastes space and could have cache implications. They were saying, no, we get to do that for efficiency purposes like that. Whereas now, N years later, that was the late 90s, the idea of address space layout randomization, for example, is in every operating system out there. And the idea of using random PIDs, the idea of using, not to get too nerdy, the idea of using random starting numbers and TCP sequences and so forth, that stuff is everywhere. And that was great. And we felt like we had some impact as far as moving in the direction of encouraging diversity, encouraging automated diversity within computing systems as they exist today. But the bigger picture of how we're not just going to try to mitigate or slow down an attack or raise the cost of an attack, but do something fundamentally different was a much tougher nut to crack. And as far as I'm concerned, nobody has cracked it yet. And for me, that eventually became quite depressing. I wasn't that interested in just doing patch around the edges and blaming users for not having done whatever they were supposed to do. I didn't publish any papers for 5 years. I got in trouble with the department because it was like, the computer security is impossible. The reason it's impossible is because the first bug costs the machine. One tiny little flaw, one buffer overflow, one unversioned symbol access, who knows? You can almost invariably leverage the first bug to taking over control of the machine. That's not an overstatement. Maybe you only get user privs. Well, whatever. It's a huge lapse. And I finally said, well, if we're going to make a serious change, what we need to do is we need to get rid of the central processor and we need to get rid of random access memory. It's the randomness of the random access memory that lets that first bug lead to the loss of the entire machine. Because as soon as you have a diversion of control, you now have this vast palette of fragments of code that you can assemble to make it do what you want to do. And that's the inherent nature of random access memory. That's what it was designed to do. So if we break that up, if we say no more central processing unit, let's have lots and lots and lots of very little individual processing units. And each of those is only going to have a limited amount of local memory. So that even if one of those little processing units happens to be close to the Ethernet card or whatever, some kind of input gets in there that causes a problem, it cannot then leverage the contents of main memory to put together a weird machine and take it over. That bug, that flaw, whatever it is going to have to go sort of make a ground assault from going from one little processor memory to the next one, to the next one, to the next one, to the next one, and so on. And the architecture you end up with is very similar to what people call cellular automata, where you have a spatially distributed array of tiny little processors, each of which has a tiny little neighborhood that's the only memory that they can access. And they are updating and trying to work together with their very nearby, physically spatial close neighbors to get some bigger job done. Is that harder to write programs for than it is for CPU and RAM? Yeah, it's way harder, and it's less efficient. But from one point of view, so what? We now know how to make gates at extremely cheap prices by the billions. Why don't we say, let's take a couple generations of Moore's Law and dedicate those to robustness, dedicate those to figuring out how to build a distributed fabric where we can write computations that are spread out over the thing, and they can grow, they can heal, they can reproduce themselves. It'll be a movable feast.
So in contrast currently, particularly in cloud computing, while there are things, which make your metaphor slightly less palatable, I think a lot of the paradigms that you're talking about already exist in contemporary cloud computing.
At the level above the single host, there is a lot of robustness work going on. And most of it is happening in the data center. And why is that? Because one company owns the whole data center. And so downtime or security flaws or whatever it is goes directly to their bottom line. By contrast, the idea of personal computing, you sell it to the user and then, who cares? So going back to what you were saying about regulatory and economic concerns, the economic model is very different in the data center. And that's encouraging as far as I'm concerned, because you get this concern for robustness, you get this concern for failover, and all of the thing, which does lead to systems being much more survivable. But at the root of it, you still got the host. And the host is non-trivial. The amount of software that's running on one host that is jointly exposed to a flaw in that one host, that's what I'm focusing on.
I know that you worked with Anton Mikhailov briefly associated with getting a GPU Moveable Feast up and running. This is something he shared with me after recording the podcast, and certainly. And do you see the potential for a virtual movable feast machine to be something which can translate into cloud computing and enable, rather than requiring hardware, to have a kind of virtual movable feast machine that can exist as scalable as you want to do your experiments on? Is that the next phase of this?
For me, it is not.
Okay.
For me, the key element of the architecture I'm building is that it has this property of indefinite scalability. You can add more and more and more and more, and there's no edge. So in cloud computing, you say, well, you can just spin up more instances. But, if they're not actually in the same region, now the latencies are very different. And so when I'm talking about measuring how fast our computer is going, how fast this distributed machine is going, I want to measure it in terms of average events per site per second. And that which gives you a sense that if you were to look at it, you'd see how fast things are blinking and moving around and, whatever it happens to be. With the cloud, with sort of GPUs in the cloud, you have these huge edges where you're going from one GPU to another, where the bandwidth crashes and the latency skyrockets like that. And that's fine. It's understandable. But as far as the model of computation I'm talking about, you're going to have to amortize your cost for having events that have to span that limited bandwidth and that incredible latency. You're going to have to factor that into your overall efficiency, the overall performance of your hardware. So I want to bite the bullet and say, let's take it down to very fine-grained and deal with the communication costs, deal with the bandwidth limitations of going not just off-chip, but off-board, but off-tile to a whole nother copy of yourself, and see how much performance we can get out of it all in. I see the advantage of what Anton is currently working on this GPU-long, this version of the programming language Ulam tailored for GPUs, is as a exploration and outreach tool. When you do cellular automata, when you do artificial chemistry and artificial life, that sort of thing, whether one knows it or not, one is strongly influenced in what one is willing to imagine based on how fast it runs. If you write some code that takes 10 minutes to do something interesting, you say, oh, okay. If you wrote something that would take 10 days to do something interesting, you just wouldn't do it. So what Anton is working on stands to provide a much higher average events per site per second for a finite box, for just a computation that fits inside one GPU. And that's all it's ever going to do. It doesn't pretend to be indefinitely scalable, but it would allow us to sort of live in the future. We might be able to get an average event rate 10 times higher, or who knows, 100 times higher, I'm not even sure, than what we're going to get out of our hardware tiles that are actually indefinitely scalable. So stuff that we could do inside the GPU MFM could be a hint at what we will be able to do in the future on actually indefinitely scalable hardware.
Movable Feast translates very well currently to cellular automata. As you've mentioned Polyworld, I think we both know a little bit about Polyworld. Would it be possible for sea monkeys to live in the Movable Feast machine?
You mean Larry Yeager's kind of sea monkey type things?
Yes.
Yeah. Absolutely. I mean, fundamentally, there's a glib answer, and the glib answer is that you can take a chunk of Movable Feast machine and use it to implement a relatively somewhat kind of traditional processor and be Turing equivalent on that processor. So you could simulate anything inside it, but that's a very unsatisfying answer because then it would have the same problem of being finite that existing machines have. So a more satisfying answer would be, how much would it take to implement something at the level of complexity of Larry Yeager's Polyworld creatures, or the ERL agents that I talked about earlier that Michael Littman and I did before Polyworld, to carry those sorts of things into the Movable Feast machine. And the answer is still definitely yes, but you're forced to deal with issues that you could sweep under the table with traditional CPU-based simulations. In particular, you're going to have more state. Almost surely you're going to have more state variables, energy, genes, health, whatever it is, than fits in one atom, in one site in the Movable Feast machine. So you're going to have to make a molecule. You're going to have to make a little spatially collected group of atoms to represent a single sea monkey. You can totally do that, but it's additional programming. And you're going to want that whole collection, that whole group of atoms to kind of move in some collective way. And you can totally do that too, but it takes a little more programming. And we are starting to get to the point of building, we're aiming at building libraries that people could just sort of pull in to help them do that sort of thing. But right now it's very early, and people are still sort of doing bespoke solutions for these kinds of things. And as far as I'm concerned, that's fine. We don't know the best way to do it. There will be trade-offs. It's not like there's going to be one data structure that's going to be perfect for all these purposes. It's going to be more like electrical engineering, where there's a zillion different AND gates. But you have to get the data sheet and see what this particular AND gate is good at, temperature, speed, pulse rate, and so forth, versus another one. And we're going to have software being similar. It's going to have all of these qualities. Like this, you would pull on this task, this kind of cellular grouping if you had something that your concern was that it could move fast. You would pull this one so that your concern was that it had a good reproduction rate, that kind of thing. So all that said, we're at the very beginning of doing all this. I make no apologies for that. If people had done this 50 years ago when they should have, we would be further down now, but better late than never. And so to build something like a sea monkey or the AL creatures from the ERL paper, you're going to have to do the work of creating a creature out of atoms. But then once you do that, you can take your hat off and you can put an agent-based hat on and think about those collections of atoms as a single flying thing and so forth. So yes, with extra work.
Professor Ackley, it has been an absolute pleasure to talk with you today. When Anton has done more stuff associated with the GPU implementation of Movable Feast Machine, it would be wonderful to have you both back on a Bird podcast to do some serious nerd rapping associated with this thing, because I think it's wonderful to have a chance to chat with you. Thanks once again for all the work that you have done for this field on YouTube, and actually, in particular, getting people that have never known about this work just slightly interested. enough to kind of dip their toe in, hopefully pick up some kind of programming manual and start getting involved with this. Thank you so much for the chance to chat today.
Well, thank you. Thank you, Tom.